What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 13, Section 1, Sequences and their Notations. Let's do it. So for question number 1, it says, discuss the meaning of a sequence. If a finite sequence is defined by formula, what is its domain? What about an infinite sequence? So when I think about a sequence, I think about a pattern of numbers that follows some sort of a formula. Now, if it's a finite sequence, the domain is going to be whatever is defined in that finite sequence. Like we might say, for example, when we're going from the first term to the 10th term, something like that. So then it's going to be defined by that boundary. Now, if we talk about an infinite sequence, what would the domain be? Well, the domain is going to be those numbers of the sequence, the position in the sequence. So it's going to be all non-negative integers, essentially natural numbers. 1, 2, 3, 4, 5, 6. That would be the domain up through infinity. Anyways, that's how you do it. Done. Is the ordered set of even numbers an infinite sequence? What about the ordered set of odd numbers? Explain why or why not. I would say both are definitely infinite. And the reason why is think about even, right? We've got 2, 4, 6, 8. I can go up to a million, a billion, a trillion. There's no end in sight in terms of the even numbers. Likewise, I could say the same thing for odd numbers, right? 1, 3, 5. I could go to 1,000,001, 10 billion and 1, etc. There's no end in sight. So both are infinite. That's how you do it. What is a factorial and how is it denoted? Use an example to illustrate how factorial notation can be beneficial. So I call factorials the multiplication countdown. So for example, 4 factorial is equal to 4 times 3 times 2 times 1, which is, of course, 24. Okay, we could keep doing this for any number, 5 factorial, 10 factorial. You just go all the way down to 1. So, and I would say the benefit of this notation is that you can just write out these numbers or these sequences of multiplication in a very short notation. And that's kind of what it says in the back of the book. But anyways, that's the definition of a factorial. That's how you do it. Done. So for this one, we're meant to write the first 4 terms of the sequence. And the first 4 terms are going to be when n equals 1, 2, 3, and 4. So we're going to plug and chug. So plug in 1 here. We'll have negative 16 over 1 plus 1, which would be negative 16 over 2. Then when I plug in 2 for the second term, it's going to be negative 16 over 2 plus 1, which is 3. So you can kind of see the pattern. Then we have negative 16 over 4 and negative 16 over 5. Obviously, we can simplify the first and the third term to negative 8 and negative 4, and leaving the other 2 terms as is. That's how you do it. Done. So for this one, to write out the first 4 terms, we're going to write out the terms when n is equal to 1, 2, 3, and 4. Then we're going to do a little plug and chug. So for the first one, we're going to have 2 to the first power over 1 cubed. Then we're going to have 2 to the second power, right? Plug in 2 there. And then we got 2 cubed. Then we're going to have 2 to the third power. 3 goes in on top. And then we have 3 cubed. And then last but not least, we're going to have 2 to the fourth power over 4 cubed. Now we can simplify this a little bit. So that's going to be 2 over 1, which is 2. This is going to be 4 over 8, which is 1/2. This is going to be 8 over 27. That can't be simplified, right? 3 cubed is 27. Last but not least, 2 to the fourth is 16 over 4 cubed, which is 64. But 16 over 64 reduces to 1/4. So those are the first 4 terms of the sequence. That's how you do it. Done. To get the first 4 terms, we're going to plug in 1, 2, 3, and 4 for n. All right, so when I plug in 1, it's 1 minus 1, which is 0. Anything to the 0th power is 1. So that first term is going to be 1.25. Next, we're going to plug in 2. 2 minus 1 is 1. Negative 4 to the 1 is negative 4. Negative 4 times 1.25 is negative 5. Next, we're going to plug in 3. 3 minus 1 is 2. Negative 4 to the second power is 16. 16 times 1.25 is 16 plus 4 is 20. Positive, and last but not least, notice the altering of it goes back and forth between positive and negative. Plug in 4. Negative 4 to the 4 minus 1, which is 3. That's negative 64. Negative 64 times 1.25 is going to be negative 80. That's how you do it. Done. To get the first 4 terms here, we're going to plug in 1, 2, 3, and 4 for n. So plugging in 1, we get 1 squared over 2 plus 1. That's 1/3. Then we're going to plug in 2. That's 2 squared. 4 over 2 times 2 plus 1. That's 4 over 5. Next, we're going to plug in 3 on top. We're going to get 3 squared, which is 9. On the bottom, 2 times 3 is 6, plus 1 is 7. Last but not least, we plug in 4. On top, we got 16 over 2 times 4, which is 8, plus 1 is 9. That's how you do it. Done. For this one, we're going to plug in n is equal to 1, 2, 3, and 4 to get those first 4 terms. So plug in 1. 1 minus 1 is 0. Negative 5 to the 0th is 1. So we get 4 over 5 for that first term. Then we're going to plug in 2. 2 minus 1 is 1. That's negative 5 to the 1 is negative 5. Times 4 is negative 20. Divided by 5 is negative 4. Now we plug in 3. 3 minus 1 is 2. Negative 5 squared is 25. Times 4 is 100. Divided by 5 is 20. And last but not least, plug in 4. Negative 5 to the 4 minus 1, which is 3. That's negative 125. Times 4 is negative 500. Divided by 5 is negative 100. Now, in front of all of these, we have a minus here, right? So that minus is going to go on at the end. So it's going to flip the sign, basically. So this is going to be negative. It's going to be positive. This is going to be negative. This is going to be positive. So these are the first 4 terms. That's how you do it. Done. So here we're going to write the first 8 terms, right? And so that's going to be n is equal to 1, 2, 3, dot, 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 all the way up to 8. But notice, we have a piecewise function. So 1, 2, 3, 4, and 5 are going to go here because this is n is less than or equal to 5. And then 5 and above, or meaning basically above 5, so we'd have 6, 7, and 8. Those are going to go here. All right, so now let's start with 1. So again, we have 1 squared over 2 plus 1, which is 1/3. That's the first term. Second term, plug in 2. That's 4 over 4 plus 1. That's 4/5. Then we plug in 3. That's 9 over 6 plus 1. That's 9 over 7. Plug in 4. That's 16 over 8 plus 1, which is 9. So 16 over 9. Last but not least, we're going to plug in 5. That's 25 over 2 times 5, which is 10, plus 1 is 11. So 25 over 11. Again, just plug and chug. Now you plug in 6, 7, and 8 down here. So we got 6 first. 6 squared is 36 minus 5 is 31. And we have 7 squared minus 5. That's 49 minus 5 is 44. Last but not least, 8 squared minus 5. That's 64 minus 5 is 59. That's how you do it. First 8 terms done. So for this one, if n is prime or 1, it's going in here. For this one, if n is composite. So let's get all the 1 or primes up here from 1 through 8. So 1 is 1, right? 2 is prime, 3 is prime, 5 is prime, 7 is prime. Everything else, which is just 4, 6, and 8 are going to go down here. That's how piecewise goes, different buckets, okay? So first let's plug in 1. So 1 minus 1 is 0, 5 to the 0th is 1. So then we just get negative 0.6. That's my first term. My second term, that's going to be 5 to the 1, right? 2 minus 1 is 1. So it's 5 times negative 0.6 is negative 3. Plug in 3. That's going to be 5 squared, which is 25. Times negative 0.6 is negative 15. Now we plug in 4 down here. 4 minus 1 is 3. Negative 2 to the 3rd power is negative 8. Times 2.5 is negative 20. Then we go back up here with the 5. Plug in 5. 5 minus 1 is 4. 5 to the 4th is 625 times negative 0.6. We get negative 375. Then we're going to plug in 6 down here. 6 minus 1 is 5. Negative 2 to the 5th is negative 32. Times 2.5 is negative 64 plus negative 6, negative 80. 7, we come back up here. 7 minus 1 is 6. 5 to the 6th times negative 0.6. And that's negative 9,375, big number. And last but not least, we plug in 8 down here. 8 minus 1 is 7. Negative 2 to the 7th is negative 128 times 2.5. That's negative 320. So here are your first 8 terms done. So what stands out to me in this sequence is each progressive number is 3 more than a perfect square in increasing order, right? So like if we have our perfect squares, think about this. We have 1 squared, which is 1. Then we have 2 squared, which is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. These are always 3 above, right? So what that tells me is a great explicit formula would then be a sub n, which means this represents the nth term in the sequence, depending on which one you want, right? Would equal n squared. We're taking our position, right? This is the first position, 1 squared. This is the second position, 2 squared. And then we're adding 3 onto that. And we can test this over here, right? We see 28 in the 5th position. So if I plug in 5, 5 squared is 25 plus 3 is 28. So that's how you do it. Done. So for this one, to get an idea of the explicit formula, I'm seeing a pattern. This is the 3rd term. This is the 5th term. So I'm guessing these denominators might be the nth term. So let's rewrite this a little bit. So I'm going to say this one is 1 over 1. Let's call this one 2 over 2. Then we've got 4 over 3. Then we've got, for this one would be 8 over 4. And then we've got 16 over 5. So now we're going to see if we can see a pattern in here. So obviously, if this is truly what we're observing, 1, 2, 3, 4, 5, then the denominator might be n. So what's happening on the numerator? We're going up by powers of 2. Look how interesting this is. Now we got 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Very interesting, right? So then we could say that this up top is going to be 2. And you might say to the n power, but the thing is, the first one, it's not a 2, it's a 1 based on how we've laid it out here. So it's going to be n minus 1, right? Because if I plug in 1 for the first term, it's going to be 1 minus 1, which is 0. 2 to the 0 is 1. Over 1, that works. Now let's try for the fifth term, right? If I plug in 5 here, I get 2 to the 4th, which is 16 over 5. So therefore, this is my explicit formula. That's how you do it. Done. So for this one, we noticed that it's always 1 on the numerator. And again, I'm going to rewrite this as 1 over 1. So then we see we got 1, 2, 4, 8, 16. Again, powers of 2. And then we're alternating from positive to negative to positive to negative. All right. So to accommodate for that negative alternating, what we often want is we want a negative 1 to the nth power. But the problem with it just being to the nth power is you see here the first term is positive, right? But if I plug in 1, that's going to be negative 1 to the 1. That's going to give me a negative 1. So we need to modify this. You can either modify it by saying plus 1 or minus 1. I'm just going to say minus 1. So that's our numerator. And then on the bottom, you can clearly see we have powers of 2. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. This is 2 to the 0th power. So again, I don't want just 2 to the n, because if I plug in 1 at the beginning, it would give us a 2. So I want to make it n minus 1. So when I plug in 1, I get 1 minus 1, which is 0. 2 to the 0th is 1. Let's test this with the fifth term right here. If I plug in 5, 5 minus 1 is 4, negative 1 to the 4th is 1. That checks out. And then plug in 5 here. 5 minus 1 is 4, 2 to the 4th is 16. So this definitely works. This is our explicit formula. That's how you do it. Done. So for this one, we're given a recursive formula and we're given the first term, and they want the first 5 terms. So we know the first term is 3. Now the cool thing about a recursive formula is you're always going to use the previous term to get the next term. So right here, for example, right? If I know that this is the previous term, this is the next term. So if I know that the first term is 3, I can literally plug it in here and I see that every successive term is going to be negative 3 times the previous term. So to get the second term, I do negative 3 times the first term, which is 3. That gives us negative 9. Then again, to get the next term, I'm going to say negative 3 times this term, which is 27. You see, negative 3 times that is negative 81. Negative 3 times that is positive 243. That's how you do it. Done. So for this one, we again are given the first term, which is negative 1, and then we're given the way to get the subsequent terms, right? So we're going to plug in for the second term, we're going to plug in obviously 2 for n, and then using that previous term down here, which is negative 1. So let's write this out. It's a little bit more complicated than the 27. So if I plug in 2 here, I get 2 minus 1 is 1, so that's negative 3 on top, over the previous term, negative 1 minus 2. So that's negative 3 over negative 3, which is positive 1. All right, let's move on to the next one. Now we're on the third term. So we're plugging in 3 for n. So that's negative 3 squared on top, right? 3 minus 1 over, and then a to the n minus 1. That's the second term. That's going to be 1 minus 2. 1 minus 2 is negative 1. 9 over negative 1 is negative 9. Okay, moving on to the fourth term. Now we're going to plug in 4. 4 minus 1 is 3. Negative 3 to the third power is negative 27 over that previous term, right? Negative 9 minus 2. That's going to be negative 27 over negative 11. We'll just say 27 over 11 as the negatives cancel out. Last but not least, the fifth term, we're going to plug in 5 up here. Negative 3 to the 5 minus 1, that's to the fourth. Negative 3 to the fourth is positive 81, because it's an even exponent, over the previous term, 27 over 11 minus 2, which I'm going to rewrite as 22 over 11. So then we get 81 over 5/11, which is the same as 81 times 11/5, right? Times the reciprocal. And 81 times 11, that's 810, plus 81, that's 891 over 1 times 5, which is 5. So those are the first 5 terms. That's how you do it. Done. So for this one, this is a recursive formula that uses the previous term and the previous term from 2 terms before, right? And minus 2. So good thing is we already have the first term. We already have the second term, which is 1. All right, now let's use the recursive formula. So it's going to be 2 times the previous term from 2 terms ago, which in this case is 1 over 24. 2 times that is 1/12, times 3 times the most previous term, which in this case is just 3. 3 times 1/12 is 3/12 or 1/4. Okay, now let's move on to the fourth term. So then it's going to be 2 times this term now, which is 2, times 3 times this term, which is 3/4. So that's going to be 6 over 4 or 3 over 2. Now again, we're going to do 2 times this one times 3 times this one. So 2 times 1/4 is 1/2. 3 times 3/2 is 9/2. So that's going to give us 9/4 for the fifth term. Okay, now we're going to run the recursive again. So 2 times this, which is 3, times 3 times this, which is 27 over 4. This is going to be 81 over 4. Okay, we can see the numbers getting bigger. And I just cleared that up to make some more room. All right, so now we got the sixth term. Now we need the seventh and the eighth term. So now to get the seventh term, it's 2 times this, which is 9/2, times 3 times this, which is 243 over 4. So 2 times 4 is 8 on the top. 9 times 243, which is 2187. So we got 2187 on top. All right, last but not least, I think we're going to get a big number here. We got 2 times this one, which is 81 over 2, times 3 times this one, which is 6,561 over 8. So on the bottom, we're going to have 16. On the top, we got to multiply these out. And we get 531,441. And those are the first 8 terms. That's how you do it. Done. So here we're going to write the first 8 terms of the sequence. And we already got term 1 and 2. So we're going to write those out here. Now to get the next terms, right? This is again a recursive formula. We're using the 2 previous terms. This is 2 terms ago. This is 1 term ago. So in this case, we've got 2 times the most previous term, which in this case is 10 plus 2. Over 2 terms ago, which is 2 down here. So this is 12 times 2 is 24 divided by 2 ends up being 12. Next, we're going to plug in 12 here and 10 down here. So 12 plus 2 is 14 times 2 is 28 over the 10 on the bottom, right? 2 terms ago. And this reduces to 14/5. Now to get the next term, we're going to plug in this here and this here. So we've got 14/5 plus 2 is going to be 24/5. And then this is going to be times 2 divided by this term, again, which is 12. So we're going to do 2 times 24, so that's 48/5 over 12, which is the same as times 1/12. These are going to cancel out to 1 and 4, so the next term is 4/5. Next, we've got this coming in here and this going in up top. So 4/5 plus 2, which would be 10/5, that'd be 14/5 times 2 over 14/5, right? Actually, these are going to cancel out and we're just left with 2. Well, look at that. So we've somehow come back to 2 for the 6th term. All right, now to get the 7th term, we're going to plug in this one here and this one up here. So 2 plus 2 is 4 times 2 is 8 over 4/5 on the bottom, which is the same as multiplying by the reciprocal, 5/4. It's going to cancel out to 2. 2 times 5 is 10. And that's very interesting because it looks like we have a pattern that's repeating. So we can presume that the next term is probably going to be 12. So those would be the first 8 terms. That's how you do it. Done. So here we want to write some sort of recursive formula. Now let's first figure out what is the pattern here, right? I see it going up by 2, then I see it going up by 3, then I see it going up by 4, up by 5. So obviously we can see a pattern, right? So what it seems to be happening is to get the next term, we're taking the previous term, okay? And in this case, think about it, right? To get to the second term, I'm literally adding 2, right? So it kind of makes sense that we take the previous term, and to get my next term, I'm adding the end value. Think about it, right? So if I'm going to the second term, I'm adding the previous term plus 2. To get to my third term, I'm adding the previous term plus 3. To get to my fourth term, previous term plus 4, etc. So a sub n equals a sub n minus 1, which is the one right before a sub n, plus n. That's how you do it. Done. So for this one, I'm seeing it's going up by 3, then it's going up by 3, then it's going up by 3. So it looks like this is just a straight arithmetic sequence. It's going up by 3 every time. So this could be pretty straightforward, right? To get the next term, I just take my previous term, a sub n minus 1, and I'm going to add 3. That's it. That's how you do a recursive formula. 3 to get the next one. Boom, done. Now we got some good old-fashioned factorials. Again, I call it the multiplication countdown. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. Let's do this mentally just for fun. 6 times 5 is 30, times 4 is 120, times 3 is 360, times 2 is 720. Of course, times 1 is just itself. So the final answer is 720. Boom, done. So this is pretty interesting. So to show you conceptually what's happening here as we do this, we don't actually have to calculate 12 factorial and then divide by 6 factorial. There's a little bit of a shortcut. So let me first write this out. So of course, 12 factorial is 12 times 11 all the way down until 1, right? That nice countdown. What about 6 factorial? It's 6 times 5 times 4 times 3 times 2 times 1. So what you're going to notice here is we got some cancellations, right? Boom, 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 and boom. Sorry, that was supposed to cancel out the 4 as well. But look what we have. So now we don't have to calculate any of that. We just got to calculate all of this, which is no small task, but it's much easier. So just for sake of time, I'm going to run this through Desmos just to get it to you quickly. So here we go, 665,280, and that's how you do it. Done. So for this one, we're going to write the first 4 terms of the sequence where n is going to equal 1, 2, 3, and 4. So we're just going to do a little plug and chug. All right, first plug in 1, we're going to have 1 factorial over 1 squared. That's just 1. Then we're going to plug in 2 factorial, which is 2 times 1, which is 2, over 2 squared, which is 4. 2 over 4 reduces to 1/2. Now what about 3? 3 factorial is 3 times 2 times 1. That's 6 over 3 squared, which is 6 over 9. That simplifies to 2/3. Last but not least, plug in 4. 4 factorial, we just throw a front on the beginning, and then it's still that same countdown. 4 times 3 times 2 times 1 is 24 over 4 squared, which is 16. And that simplifies as well. Divide top and bottom by 8 to 3 over 2, similar to 2/3. But anyways, that's how you do it. Done. So for this one, to get the first 4 terms, we're going to set n equal to 1, 2, 3, and 4, and do a little plug and chug. All right. So on top, here's what I'm going to do actually. I'm going to write this out like this. We're going to make it all fractions, and then we'll simplify afterwards. So on the top, we're going to have 1 factorial, 2 factorial, 3 factorial, and 4 factorial. So let's write that out. So 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. And 4 factorial is 4 times 3 times 2 times 1, which is 24. All right, now we plug it in on the bottom. Plug in 1. 1 squared is 1 minus 1 is 0 minus 1 is negative 1. Plug in 2. We got 4 minus 2 minus 1, which is 1. Plug in 3. We got 9 minus 3 minus 1, which is 5. And 4 is 16 minus 4, which is 12 minus 1 is 11. Now do some simplification. That's negative 1. That's 2. We'll leave those impropers as is, and that's how you do it. Done. So for this one, they want a graph of the first 5 terms. So I'm going to show you what that looks like actually in Desmos. So first what I'm going to do is I'm going to make a little table, n and a sub n, like so. And of course, the first 5 terms are 1, 2, 3, 4, and 5 for n. Now let's plug and chug, right? So I plug in 1, negative 1 to the 1 is negative 1, over 1 is negative 1, plus 1 is 0. Plug in 2. Negative 1 squared is 1 over 2, which is 1/2, plus 2 is 2.5, or 5/2. Plug in 3. Now we're going to have a negative 1 on top over 3. Negative 1/3 plus 3 is 2 2/3, which is 8/3 as an improper. Plug in 4. We get 1 over 4 plus 4, which is 4 1/4, or 17/4. Last but not least, plug in 5. We get negative 1 over 5, which is negative 1/5, plus 5, which is 4 4/5, or 24/5. Now we're going to plot each of these in Desmos, so you're going to see what it looks like. So here I've just used x for n and y for a sub n, but it's the same idea. These would be the 5 points. That's how you do it. Done. So for this one, we got a recursive formula, it looks like. So let's go ahead and plot out the first 5 terms here. So again, we're going to have 1, 2, 3, 4, and 5 for our n values. And it says the first one is 2. Now to get the second one, right, we're going to plug in 2 for n, but obviously it's just the previous term. So the previous term is 2 negated is -2 plus 1 is -1 squared is 1. Now to get the third term, plug in the previous term, that's -1 plus 1 is 0. 0 squared is 0. Plug in the previous term here to get the fourth term. -0 is 0 plus 1 is 1. 1 squared is 1. And now it looks like we're going to go in a loop back and forth between 1 and 0. Plug 1 in. -1 plus 1 is 0. 0 squared is 0. Now let's plot this in Desmos. All right, here are the 5 points. That's how you do it. Done. So for this one, first, we're going to get the 5 points. We're going to make a little table n and a sub n. And we're going to start with 1, 2, 3, 4, 5. We got some factorial action happening here. All right. So first and foremost, we're going to plug in 1. On top, we're going to get 2 factorial over 1 minus 1 is 0 factorial. Now, you might think that 0 factorial is 0 and this is undefined. That's actually not true. Fun little fact, 0 factorial is actually 1. So 2 factorial is 2 times 1, which is 2. 0 factorial is 1, so we get our first term as 2. Now the next one, we're going to plug in 2. So we get 3 factorial over 1 factorial. 3 factorial is 3 times 2 times 1, which is 6 over 1, so we got 6. Next, we're going to plug in 3. So we get 4 factorial over 2 factorial. Now, remember, 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. So if you see on top, right, we got a 2 and a 1, and on the bottom we got a 2 and a 1. Goodbye, goodbye. I just have 4 times 3, which is 12. Makes it a little simpler. Now plug in 4. We're going to get 5 factorial on the top, 3 factorial on the bottom. So again, the 5 times 4 is going to be left. 3 times 2 times 1 is going to cancel out. And that leaves us with 5 times 4, 20. Boom, done. Last but not least, 5 factorial. This one I'll write out because it's a little longer. So we get 6 factorial over 4 factorial. So once again, 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1. So you can see that pattern. Goodbye, 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 goodbye. What do we have left? 6 times 5. That's 30 for the win. And now let's graph it out on Desmos. So those are the points. That's how you do it. Done. So for this one, it says write an explicit formula based on these 5 points. So let's write this out in the table with n and a sub n for the term. So we've got 1, 2, 3, 4, and 5. And of course, we've got 0.5, which is a half. Then we got 1, 2, then 4, then 8. So what this looks like to me is powers of 2, right? 2 to the -1 is 1/2. 2 to the 0th is 1, so on and so forth. So for this sequence, again, we want to plug in 1, though, and we want to get 2 to the -1. So if I'm thinking about it, I would say 2 to the n. That would be my first instinct. But again, 1 should give us 2. 2 would give us 4. So we can see we have to offset it. So instead of doing just 2 to the n, what if I did 2 to the n minus 2? Now if I do this, if I plug in 1, I get 1 minus 2, which is 2 to the -1, which matches up. Plug in 2, we get 2 to the 0, which is 1. Plug in 3, we get 2 to the 1, which is 2, and so on and so forth. So there's the explicit formula. Done. For this one, we're meant to write a recursive formula. So let's write these out so we can see them a little bit more clearly. So for 1, we have 6, then 7, then 9, then 13, and then 21. So for this one, if we're trying to get a recursive formula, it's not super clear right off the bat as to how am I going to always manipulate the previous term to get the next one. But what you might notice is one of the patterns is if I double this and minus by 5, right? 2 times 6 is 12 minus 5 is 7. And then you'll see that pattern repeat. 2 times 7 is 14 minus 5 is 9. 2 times 9 is 18 minus 5 is 13. So we see that pattern repeat. Therefore, a sub n equals the previous term doubled and then minus by 5. And that's your recursive formula. Again, recursive is to get the next term from the previous term. That's how you do it. Done. Find the first 5 terms of the sequence a sub 1 equals 87 over 111. Okay, and then we have this nice recursive formula. Now, we can use our calculators, what they're saying, use the fraction feature to give fractional results. Let's go ahead and use Desmos, in fact, to output all of our answers. So what I did here is I kind of created that recursive formula, 4/3 times whatever the first term is plus 12 over 37 to get the second term. So the second term is 152 over 111. And the way I got it to display as a fraction in Desmos is I click this little button right here, right? If I unclick that, it shows it as a decimal. So there's the second term. Then I plugged in the second term to get the third term, plugged in the third term to get the fourth term to get the fifth term. And that's how you do it. Done. Find the first 5 terms of the sequence a1 equals 2, and this is the recursive formula here. So my first term is 2, plug it in here, a sub n minus 1. So that's my previous term, which in this case is 2. 2 minus 1 is 1. 2 to the 1 is 2 plus 1 is 3. Now I plug it in here. I've got 3 minus 1, which is 2. 2 squared is 4 plus 1 is 5. Then I plug in the 5 here. 5 minus 1 is 4. 2 to the 4th is 16 plus 1 is 17. And last but not least, plug in 17 now. 17 minus 1 is 16. Now we're going to need Desmos. 2 to the 16th is 65,536. And 65,536 plus 1 is 65537. That's how you do it. Those are the first 5 terms. Done. Find the 10th term of the sequence where we have the first term is 2 and then we have this recursive formula. So let's figure that out. So we have to go step by step because it's a recursive formula. So we got 2, then we have to find the second term. So I'm going to plug in the first term. So it's the n value is 2. The previous term is 2. 2 times 2 is 4. And I'm going to write in the n values up here so we can keep track. I'll keep them in red. 6, 7, 8, 9. And we're trying to get the 10th term. So now I get the third term. I'm going to plug in 3 times the previous term, which is 4. That's 12. And you can see the pattern. Then we do 4 times the previous term, 12, which is 48. 5 times the previous term, which is 240. You see these are getting pretty big pretty quickly. Then we got 6 times that, which is 1200, 1440. Let's write it down here so we have more room. Then we have 7 times that, which is 9800 plus 280, which is 10,080. Now I'm going to do the rest in Desmos because the numbers are pretty big. We have 8 times that, and we get this. Then we have 9 times that, and we get that. And then our last one will be 10 times this, which is this number. So our 10th term is 7,257,600. That's how you do it. Done. So for this one, we have an explicit formula, and we're meant to find the first 6 terms of this sequence. Now, because we got some big exponents and a lot of decimals, we're going to do this in Desmos. Let me show you how. So what I did is I entered the explicit formula as a function in Desmos, and then for the different n values, I used x, and I set it equal to 1, 2, 3, 4, and 5. Now we're going to see the intersection points, and the y value is going to be the terms of the sequence. So the first term would be 0.042, second term would be 0.146, third is 0.875, fourth is 2.385, and fifth is 4.708. So that's how you do it. Done. List the first 4 terms of the sequence, and since we got some funky numbers with the 5.7 and we got some factorial stuff going on here, we're going to plug this into Desmos. So here's how we're going to get the first 4 terms. Again, I put in the explicit formula as a function into Desmos, and then I set x equal to 1, 2, 3, and 4, and we're going to look for the intersection points, and the y values will be the terms of the sequence. So here's the first, second, third, and fourth, right? So we got 5.975, 32.765, 185.743, and 1057.25. Now, they did put a 5th value in the back of the book, but of course they only asked for 4, so I'm just providing the first 4, but that's how you do it. Done. Consider the sequence defined by a sub n equals -6 minus 8n. Is this a term in the sequence? Okay. So this is an explicit formula. So to figure out if this is a term in the sequence, we're going to plug this in and see if we get a nice integer value for n. It's got to be a positive integer value. Okay, so let's check it out. -421 is equal to -6 minus 8n. We're going to add 6 to both sides like so. -421 plus 6 is -415. So as you can see, right now this equals -8n. You know we're not going to get an integer, but we'll do the division anyways, and I say that because it's an odd number here, right? So 415 divided by 8 is 51.875. Again, not an integer, meaning it is not a term in the sequence. No, that's how you do it. Done. Find a recursive formula for this sequence. 1, 0, -1, -1, 0, 1, 1, 0, -1. Hint, find a pattern for a sub n based on the first 2 terms. So what it appears to be is if we have these as our first 2 terms, it looks like it's the second term minus the first term, which means it would be like a sub n minus 1 minus the preceding term, which is a sub n minus 2, and that would equal a sub n. And we can test this out later, right? Let's say we get to this point. To get this term, we're doing this minus this, and that is indeed 0. And then let's test out the next term, negative 1. We'd get 0 minus 1, which is indeed negative 1. So this would be the recursive formula. That's how you do it. Done. So this has to calculate the first 8 terms of the sequences, boom and boom, and then make a conjecture about the relationship between these two sequences. And then what it's saying in 71 is we have to prove the conjecture. And the conjecture is that this is equal to this. So how do we prove that? All right, so let's kind of write this out and see if we can simplify it and get it down to this. So think about n plus 2 factorial. Whatever n is, right, that's going to be, it's a multiplication countdown. It's going to be n plus 2 times n plus 1, right? We're kind of decreasing, plus times n minus 1 times n minus 2, et cetera, until we get down to 1, right? And on the bottom, we have n minus 1 factorial, which would be n minus 1 times n minus 2, et cetera, dot. Well, you can see that everything from n minus 1, n minus 2, and on, they're going to cancel out because they're going to exist on the top and bottom. So boom, 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 and everything else is going to go away, meaning we're left with just this. Now, if we FOIL this out, let's first multiply the n in. We got n plus 2 times n squared plus n. And as we distribute and FOIL this out, we get n cubed first, plus n squared plus 2n squared plus 2n. And when we combine like terms, we end up with n cubed plus 3n squared plus 2n. So that's the proof of this conjecture. That's how you do it. Done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.